So far we talked about multiple cash flows, even or uneven for up to 10 periods. Imagine if you have to find the present value of a 25-year-old loan with monthly payments. How many calculations you have to do for each cash flow? About 300. That's where annuities come into place to help us calculate present or future values when we have such situations. So if we have a string of known finite number of equal payments that occur at regular intervals of time, we have an annuity. Think of annuities as pensions or loans. There are two types of annuities: ordinary annuity and annuity due. An ordinary annuity or end of period annuity is an annuity where the cash flow occurs at the end of each period. For example, the bonds, consumer loans, and home mortgages. On the other hand, an annuity due or beginning of period annuity occurs when the cash flow is paid at the beginning of each period. For example, leases or rents. So basically the difference between the two is one extra payment. A perpetuity is similar to the annuity. However, the number of periods is unknown in the sense that the payments continue forever. So an infinite series of equal payments at regular intervals of time is a perpetuity. Note that with both annuities and perpetuities, the cash flows or the payments must be equal. We cannot have uneven cash flows. Also, the other rule is to have regular intervals. We cannot interrupt the cash flows for a few periods, then start again. The cash flow must occur every period. Otherwise, there is no annuity. And these are the future value formulas for the ordinary annuity and annuity due. Note the difference between the two formulas. Because the annuity due payment starts at the beginning of period, there is one more compounding calculation performed by adding 1 plus R at the end of the big bracket of annuity due. And the example shows the difference between the two streams of cash flows. The annuity due future value will always be higher than that of the ordinary annuity because of that extra compounding calculation that needs to be performed. These are the screenshots for the future value functions in Excel. Note that the only difference between ordinary annuity and annuity due in Excel is that for annuity due we must specify number 1 as the type of annuity. That's how Excel knows to calculate annuity due to perform that extra compounding calculation. And here we have the formulas to calculate the present value for both types of annuities. Again, the present value of annuity due is always higher than that of ordinary annuity because the present value of annuity due is just the present value of an ordinary annuity multiplied by 1 plus R. These are the screenshots for the present value functions in Excel. Again, note that for annuity due calculation you must specify type 1. Now I want you to take some time to do this quick quiz, but you have to read the question carefully. Let's read it together. Your son is 21 and wants to receive $5,000 per month in retirement. In his retirement, he expects the interest to be 0.75% per month. He thinks he'll need the income for 25 years. How much does he need to have in his account at retirement? So what are we trying to find here? Is it a present value or a future value? Note, because we have $5,000 per month in retirement, we are talking about an annuity, $5,000 per month regular payments. So think about it. Is it a future value or a present value of annuity? We are trying to find the present value. You might be inclined to say future value because the retirement is in the future. Yes, the money is needed in the future, but it's needed when the son retires. So actually we're trying to find the present value of his pension. Given that the interest rate specified is per month and the payment is also specified per month, remember we have to transform the remaining of the variable, the years, into monthly periods. So 25 years multiplied by 12 is 300 months. So when we calculate our present value, we have to use 300 as our n. Please do the calculation and see if you can get this answer. The present value should be $595,808. So, in other words, this is how much super your son needs to accumulate by the time he retires so he can have a pension of $5,000 per month after for the next 25 years. And last, we present the formulas for perpetuities. Note that only we have present value formulas. Why don't we have future value formulas for perpetuities? The reason is that the cash flow never ends. It continues forever, and that's why we generally use perpetuities to value shares, as it is assumed equity has no maturity, it is long-lived. However, an infinite series of cash flows can have a finite present value, a known present value. Because of the time value of money, each payment is only a fraction of the last. The first formula is a present value with no growth, meaning that the cash flows are constant. We said that an example of such perpetuity is a preference share, where the company promises to pay the same dividend forever. We use this formula to value such shares as we have in the first example, where a company pays a dividend of $3 and the required rate of return is $10. The value of such shares is $30. The other formula, a growing perpetuity, is an annuity in which the cash flows continue forever. However, those cash flows grow at some constant rate. This is usually used in ordinary share valuation, where dividends increase with the level of earnings, as it is illustrated in the second example, where we're assuming that the earnings and dividends of the company will grow at 6% a year over the long run. We apply the growing perpetuity formula and we find the value of those shares to be $75. In the next module, we will use these formulas again in share valuation. And now we briefly discuss the effective annual rate. For example, if you have to choose between an investment that pays 10% per year or an investment that pays 10% per year compounded semi-annually, which one do you take? You might say that it doesn't matter because 10% per annum compounded semi-annually is just 5% per 6 months. That's where the effective annual rate comes in. This rate enables us to compare interest rates that have different compounding periods. the effective annual rate takes this 10% compounded semi-annually and transforms it into the actual rate per year, taking in consideration the effect of compounding. In fact, the effective annual rate of 10% compounded semi-annually is actually 10.25%. This is very useful if you want to compare two alternative investments with different compounding periods, and you need to compute the effective annual rate and use that for comparison. This concludes Module 3.